Washington State University. Go Cougs!
Welcome back to the course on behavior analysis from mobile sensor data. In this course segment, we will look at activity learning and specifically how to extract a feature vector from sensor data collected via mobile devices, in this case, a mobile phone. As we mentioned previously, our activity learning discussion will focus on two components. The first being feature extraction, or how to extract a feature vector that represents a single data point from mobile data, and then activity recognition, how to automatically recognize activities that are being performed based on these data points collected from mobile sensor data. Earlier in this course, you learned how to write a mobile app that would collect sensor data from a phone, like you see on the screen here. Now we need to look at how to extract features from these sensor values that would describe a single data point that can ultimately be used for modeling and recognizing activities. What we are looking at here are actual sensor values that were collected from a user via an app such as the one that you designed. Our goal in this particular course segment is to extract features from what we see here of the mobile phone data. This set of data, as you can see, contains values represented by 4 fields: the date of the data collection, the time, the sensor, and the value. Based on an app, like the one that we showed in the previous course segment, data can be collected for any amount of time. In this case, we are collecting it for 5 seconds at a time. Thus, these values are all collected over 5 seconds. So you can see we have a value for each of the sensors that our app is collecting for the same date and time for 1 second. And the next set of values represents the same date 1 second later, the 3rd second, 4th, and 5th. The particular sensors that we are collecting data from include yaw, which, as you can see, is rotation in one direction, pitch, rotation in another direction, and roll. Each of these values will be collected 1 time per second according to the app that we are using. In addition, we will collect data on acceleration or change in velocity for the X, Y, and Z directions of the phone. We will also capture location information, and on your mobile device, this could be through some combination of GPS, or the Geographical Positioning System, GSM, Global System for Mobile Communication, and signals from Wi-Fi hotspots. This particular latitude and longitude and altitude correspond to a Starbucks restaurant located in Pullman, Washington, as we see on the map. Additionally, we are collecting course, which has a value from 0 to 360, indicating the direction that the phone is facing, as we see on this compass here, and the speed with which the phone is moving in that particular direction. Looking at the values that we see here for yaw, pitch, roll, acceleration, location, course, and speed, we might be able to infer that a person is sitting at the table eating because they are at a Starbucks. It is late in the evening. The phone is not actually changing location much during the course of the data collection. And based on this person's context, this is a routine part of their behavior. Our next task is from this data to extract features that would provide enough information to automatically recognize that this is, in fact, an eating activity. As we described in another course available through this program, Behavior Analysis from Ambient Sensor Data, we have a similar problem in behavior analysis from mobile sensor data in that we want to define a context window. We can assume that data is being collected continuously from our mobile device, whether it be a phone, a watch, some other kind of wearable sensor. And since it is defined continuously, our goal is to determine at any particular point in time what the individual is doing in terms of an activity label. So we need to first determine how much of that data we're going to use as a context for labeling an activity. To define a context window, there are several approaches we can take. We can either pre-segment the data if we have some way of knowing where the beginning and ending of an activity is. For example, if there are scripted activities, we may have recorded when each activity begins and ends, and then we only need look at the window of data corresponding to a single activity. If we don't have such segmentation available, we might instead choose to use a sliding window in which we are going to define the context as a certain number of seconds of data or a unit of time for which we are going to collect the data and extract the features to represent a single data point. And these windows can overlap with each other or be constrained to be non-overlapping. As you can tell from the data that we showed initially, we are defining our window to be 5 seconds of sensor data in length. We will make it non-overlapping in this particular case, and our sensor polling rate is one set of values per second. So we have 5 seconds of data, and for each second we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 values. So we have 55 values from which to extract features. The first set of features that we will describe that we can extract from this 5 seconds of data are features that describe the window as a whole. So the values that you see on the screen represent our context window, all the values collected over 5 seconds. We can capture, for example, the date on which the data was collected. And it could be the absolute date, or it could be the date of the year, number of days that have elapsed since January 1st of the same year, which in this case is 251. We might also want to capture the day of the week because many individuals have routine behavior that is dependent on this function. They may do something different on Monday than they do on Tuesday. They may do something different on weekdays than they do on weekends. And we will constrain our feature vector in this particular case to have all numeric values. So instead of representing the day of the week as a string, in this case Wednesday, we will represent it as a number with Sunday being 0 and Wednesday thus being the value 3. Additionally, we can collect features representing the time of day in which this data was collected, and this could be collected at different granularities. So we represent it, in our case, in terms of the number of hours past midnight, which is 21 in this case, the number of minutes past midnight, and the number of seconds past midnight. We show these 3 values on the screen here. Next, we can gather a large number of statistical features representing our numeric-based sensor values. And we will demonstrate these statistical features for one sensor value, in this case, Ya, but we can repeat the process for all of the other 10 sensor names as well. So we've summarized at the top of the slide here the Ya values collected over the 5 seconds, and the statistical features representing Ya over this duration can include the maximum and minimum values observed, the sum of the values, the mean and median. We can also compute standard deviation, where in this case, S sub I represents each one of the particular values, and S bar represents the mean of the value. And in addition to standard deviation, we can also compute mean absolute deviation, where the absolute value of the difference between the point and the mean is computed rather than the square, summed, and then divided by the number of points that we have observed, in this case 5. And we can compute the median absolute deviation, which is similar to mean absolute deviation, except the difference is computed with respect to the median of the set of values rather than the mean. Another set of statistical features that we can consider include zero crossings, mean crossings, and interquartile range. Let's again focus on the set of yaw values that we collected over 5 seconds. Zero crossings looks at the number of times the plotted values over the 5 seconds crosses the median line. So if we plot these values over time, as indicated by the red line, we're going to compute how many times that plotted line crosses the median, which is indicated by the dashed line. In this case, 1 time. If we had been looking at a value such as acceleration, and there were a number of crossings, this might indicate shifts between rapid and slow movement that could be helpful in distinguishing activities such as walking from running. In addition to computing zero crossings with respect to the median, we can also compute mean crossings, which performs the same task with respect to the mean line rather than the median. In addition, we compute interquartile range, or IQR, which gives us a sense of the statistical dispersion of the observed values. To compute this, we first sort the list of observed values in non-decreasing order, and here we have them for our yaw values collected over 5 seconds from the smallest value to the largest value. IQR, or the interquartile range, looks at the difference between the 75th and 25th percentiles, where percentile indicates what value you're looking at different positions in the sorted list. So the beginning of the list would be the 0th percentile, end is 100th, middle is 50th. We compute the values at the 25th percentile, which is this one, the 75th percentile over here, and look at the difference between them, which is this value 0.5343, and that gives us a sense of scale for this set of values. Additionally, we can compute skewness and kurtosis, and that gives us some sense of the shape of distribution of values that we're observing. Skewness gives us a sense of the asymmetry in the distribution of values. As you can see by these diagrams down here, in a case where there is a lack of symmetry and it's skewed to the left, the skewness would be greater than 0. Skewness to the right indicates a skewness less than 0, and perfect symmetry would give us a skewness of 0. Here's the formula for skewness, where n represents the number of data points, in our case 5, s sub I represents each individual value, and s bar represents the mean. We can also look at kurtosis, which is the amount of peakiness or flatness in values. As you can see by this diagram here, there's a difference between C, which is fairly flat, in comparison with A, which has a large degree of peakness, thus its kurtosis value would be larger than that of B or C. And here's the corresponding formula for calculating kurtosis. There are many features that could be included in our vector that describes the data that we've collected from a mobile device. We are not going to be able to cover all of them in this discussion, but another set that we can touch on are signal processing features that are commonly used in signal processing applications, which include signal energy, which essentially represents the area between the plotted curve of values and the time axis, and can be computed in the discrete value case as the sum of the squared values. The log energy is the sum of the log squared values, and signal power is the average of the sum, or average of the squared values. In the continuous valued case, instead of computing the sum, we should be computing the integral. Other features that we could consider for our feature vector are relational. They look at the relationship in values either between different features or between values of one feature at different points in time. So we may have some sensors that have multiple axes, such as acceleration in the X, Y, and Z directions. The correlation between the values of multiple axes might indicate that there's movement going on in multiple directions, and thus give us a better sense of how that movement is occurring throughout the space. So in this case, we can compute the correlation between acceleration in the X and Y axes and do the same thing for X and Z and for Y and Z. In this case, we just show the correlation between axes X and Y, which is the value shown on the slide here. Similarly, we can look at autocorrelation, or the correlation between one variable at different points in time, so between the current time and time minus a lag value. So in the formula for autocorrelation, we indicate with a subscript the lag value that we are using. In our particular example, we'll look at autocorrelation with a lag of 1 or subscript of 1, and we compute that for Ya, as seen here. That lets us know what the relationship is between the value over time with respect to the observed values. While there are many other features that can be generated, we end with a discussion of features that can be generated from the location values that are observed from our phone that we've shown here: latitude, longitude, altitude, course, and speed. One such location feature is the heading change rate. In addition to wanting to consider the direction that the phone is facing, we might also be interested to know if there was a change in this direction throughout the course of the data collection. Another is stop rate, where we consider the percentage of points in the collected sequence of data that exhibited a significant drop in velocity, as might happen, for example, if somebody was driving in a car and came upon a stop sign or traffic signal. Additionally, we might want to know the overall trajectory from the beginning of the data collection to the end, in addition to course at each second of the data collection. As you can tell, all of these will require some kind of threshold value to determine at what point there is a significant change in course, velocity, or trajectory. Finally, while these values give us some sense of where a particular user is at, they're going to be very specific to each user. The fact that this set of coordinates reflects that a person might be at a Starbucks doesn't let us know for someone who lives in another city that they're at a Starbucks as well, eating or drinking coffee. Therefore, we might want to add to our vector features that describe a more generalizable sense of location. It could be the location type, as can be obtained through reverse geocoding, which would let us know that this person is at a restaurant or cafe. We can also compute the normalized distance that is typically traversed for an individual over multiple days. With that information, then we can look at the distance from this particular location to the user's mean location, or where their particular center of activity is located. So for the 5 seconds of data that we collected in this particular example, the feature vector, just based on those features that we've described and only based in the statistical case on yaw values, is shown here. Once we start adding similar values for all of the other sensors and expand the set to include more contextual information, this feature vector can grow arbitrarily large. In the next segment, we will discuss how to use this feature vector to learn a mapping from the vector to an activity label.